So it's my great pleasure to announce the second speaker for today. It's Dierk Schleicher from Aix-Marseille University, and he will tell us an interesting story about post-singular finite entire functions, about the combinatorics, complexity, and Thurston theory.
Thank you, Kostya, and of course, thanks to all the organizers for bringing all of us here. So I will talk, in some sense, understanding complexity of Julia sets. The first half or so is about rational maps, more precisely about complexity of polynomial maps. I will discuss complexity in terms of, well, by accessibility dimension and how to estimate this. And then a related, very closely related concept is that of core entropy that Thurston introduced just about the time of my first visit to India. And ever since then, we've been discussing this. So the first two sections are about results for polynomials. Before then, I want to move on and try to extend some of this into the transcendental world. But a large part of the talk is exploring how to do it, what the difficulties are. The transcendental world, as is well known, is rather different from the rational world. Trying to find the right definition and a reasonable setup that works, even though you don't have all the tools available that are used to for polynomials. So how complicated is the Julia set of a polynomial? Well, one way is to look at branch points. Yes, of course, infinitely many branch points. But how can you distinguish the branching? Some Julia sets are just an interval. Some are close to an interval. Some have more branching. And you can try to count how much branching there is and how many points are branched or not. So let me define a point in the Julia set is biaccessible if it is the landing point of at least two dynamic rays. So you take a point here, there's a dynamic ray coming from one side, there's a dynamic ray coming from the other side that land at the same point. So such points are called biaccessible, as opposed to endpoints like here or here, points that are landing points of just one ray. And of course, there can be branch points when you have three or more rays landing, such as this one, and then you have 1, 2, 3 rays. Well, now in order to make this precise, the first question is, well, it's well known that not all rays land. There could be a ray that kind of wiggles and cannot really decide at which point to land. But it's well known that those rays that don't land form a set of angles of dimension 0, so they don't really play a role. You can easily ignore them. Or you can rephrase this in terms of fibers or so in which they accumulate. This is not really a relevant issue. On the other hand, 3 or more rays land together only at countably many points. So in general, there are only countably many rays that are affected by 3 or more rays that land together. So that is not relevant also. So the real interesting question are those points or those angles that land exactly in pairs. There's been old work, Anas Dunix, Tasnanov, Said Zakeri, who proved that biaccessible points have 0 harmonic measure. This has not worked together, but they worked in different generality, what properties of the Julia sets they're using, such as local connectivity or not. So successive improvements. And harmonic measure is really a property of the angles. Yes? And yeah, so this is, you see, I ran out of space. Yes, but there will be a slide with a theorem later on where it say it. It should have been said. Yes, apologies and thanks for the correction. But this is indeed the one exception that Julia said can be like z squared minus 2. John Smiley is here. He asked me about this particular map in my qualifying exam back in Cornell in the old days. Okay, so this is, yeah, so maybe certain things, can we avoid those exceptional maps, please, for the rest of the talk? Thank you. So what did I want to say? So harmonic measure really is the measure of the external angles that land or of the corresponding rays. So this result can be reinterpreted as saying that if you take the space of external angles, then the measure zero set will, except for the interval I'm trying to learn here, the set of measure zero will land with others, and the rest, most of them are endpoints. So I define an angle to be biaccessible if there is another angle so that the two rays land together at the same point, and the biaccessibility dimension lives on the circle of angles, and it's the Hausdorff dimension of those angles that are biaccessible. Since that's a subset of the angles, it's somewhere between 0 and 1. And here, so Roman, you see, I had taken this a bit too late, but you're right. So this dimension is always strictly less than 1, except when the Julia set is an interval. So this result does not require any topological property, no local connectivity, no anything. Technically can require the Julia set is connected, but even that doesn't really play a role. So this is quite a bit stronger than the previous result, not only because it states the exception, but also because if the dimension of biaccessible angles is less than 1, then the one-dimensional measure is 0. So harmonic measure is 0. So this implies the previous results. Of course, it was a couple of years later. Philipp Mehrkamp, by the way, was a bachelor student at the time, and then went on for PhD study in Cornell with Guggenheim. Okay, now we can try to estimate the biaccessibility dimension. Okay, so we tried, so there are some cases when this dimension must be 0. For instance, when the Julia set is a topological circle, then you have nothing biaccessible. Or even in cases when the Julia set has only many cut points, the duo Dirac and whatever, are trivial examples when the Julia set has or must have biaccessibility dimension 0. But of course, there can be other cases. These are just sufficient examples for dimension 0. There are other cases, for instance, the real Feigenbaum polynomial has infinitely many cut points, and still the dimension is 0. And that's been work with Henk Point that we did at the beginning of the millennium. Can I say that? So the biaccessibility dimension of a quadratic polynomial with connected Julia sets you're in the Mandelbrot set is 0 if and only if you're in the main molecule of the Mandelbrot set. Maybe let me use 2 colors. So this is the main molecule, while the Mandelbrot set, of course, extends further out. So it's 0 on the closure of the main molecule. I'm not sure whether the molecule should be closed by definition. It's 0 if and only if you're in the closure of those. And you have continuity, well, not only at the locus of where it's 0, but also continuity towards 0 from the outside. And this continuity implies that the closure must be 0 and that the Feigenbaum has biaccessible dimension 0, even though you approach it from the left with positive entropy. Can we turn off the light perhaps again? Thank you. So we have some more precise estimates that I don't really want to get into. Needing sequence and combinatorics will come up later on. And just to show, when you know something about the combinatorics, one can give quite precise estimates on the biaccessibility dimension. There are 2 sets of lower and upper bounds. One of them is very close when you're at the antenna tip of the Mandelbrot set. So this is the only point where you get an interval. The biaccessibility dimension is 1. And on the left-hand side, you measure how fast you converge to biaccessibility dimension 1. And the others give you a precise quantitative estimate how fast you converge to biaccessibility dimension 0, purely in terms of combinatorics, which is the leading sequence. I don't want to define it now, it will come up later. But just knowing the combinatorics tells you quite a bit about estimates of the biaccessibility dimension, at least close to value 0 and close to value 1. This old work with Henk back in the days. So now let me move to a related concept, core entropy. And this goes back to the very first result we talked about of Michailowicz. We must imagine a young boy picking cotton in the fields and proving theorem along the way. So every degree D rational map has topological entropy log D on the Julia set. Topological entropy is kind of the growth rate of how many combinatorially distinct orbits you can have, and the exponent of how many orbits there are, that is the entropy. This is a wonderful result that has one great strength and it has one weakness. The strength is that it's constant, depends only on the degree. So all maps have the same entropy, which is very nice and very beautiful. The weakness is that all maps of the same degree have the same entropy. So you cannot distinguish maps from the same space. So it will not help you to understand parameter spaces because the result is so nice and uniform. Here is one case when the people from real dynamics know a bit more than we do. When real people look at quadratic polynomials, the picture typically looks like something like this. And then you have a dynamical interval, which is this. And you can look at the entropy of this maps. And here, depending on different maps, you can have small entropy, you can have entropy log 2, and anything in between, which is a continuous result, even though this can be quadratic polynomials in whichever scaling just as well. And the difference is they don't look at the complex, they only see part of the world. So we complain the real people miss all the information that sits in the complex plane. But in this case, this is interesting. If they were looking at the entire complex plane with the Julia set, they would get Ljubich's log 2. But here they have an interesting, a natural dynamical invariant interval. And the restriction to this interval tells you something about entropy. It's monotone and continuous for real quadratic. So this is an interesting quantity that you get in the real world and not so much in the complex. So then Thurston came about, thank you, and introduced around 2010 the concept of core entropy for a post-critically finite complex polynomial. So if you have a post-critically finite complex polynomial, you have a Hubbard tree, which is a natural analog to the invariant dynamical interval. It's a connected tree that contains the orbits of all. It's invariant, contains all the critical points. So in some sense, it's the smallest invariant subset of C, but contains all critical points if you do it right. So it is a natural definition. And here you can define core entropy. And then it's again between 0 and log 2, or log D for the degree of the polynomial. So this is a natural replacement for the dynamical interval, except with one weakness. You have a Hubbard tree only for post-critically finite polynomials, while the dynamical interval exists for all real parameters in that setting. So this is the natural starting point. And then Thurston proved that in this case, post-critically finite polynomials, core entropy is the exact same thing as biaccessibility dimension, except for scaling factor log 2. The biaccessibility dimension is between 0 and 1, the entropy between 0 and log D, multiplied by log D, and then these are exactly the same thing. So I write here two names. Wolf Jung worked it out, but I have an email from Xavier Boeuf from 2011. I just checked this last night. Then Xavier told me, oh, Bill Thurston must have known about it. And the next day, oh yes, he knows about it. Xavier visited him in hospital. Thurston was already sick at the time. And asked him, and out of the hospital, he got the message, yes, this is the result he has. So I don't have a written proof other than this email from Xavier that Thurston had this equality. So without knowing it, the results that we had worked on earlier were results on core entropy back in the days. Thurston wrote me an email at some point saying, I'm investigating this concept. And initially, I wasn't sure. I had nothing to say. Why is he asking me? Why is he sending him an email asking me about it? Until I realized later I had worked on it. So Thurston asked the question around 2010, whether core entropy depends continuously on the parameter, at least for quadratic polynomials. So I was in Cornell at the time, and Hubbard didn't believe it. So there was a bet for $20 whether or not this was true. Bill was in favor, Hamill was against. And then Dima was around at the time. And we settled this enough in the semester that I saw Hubbard pass on the $20 bill to Thurston. So to me, that was the moment when the conjecture was settled. Hamill voluntarily giving out money. I mean, you must imagine that's a rare moment. No, he's very generous, but still there was a special moment. Julio Chotze also had a proof, but surprisingly, it's in the thesis of Chris Penrose. Of course, there's only one person who manages to reach Penrose's thesis, that's he himself. And he told me a year ago that it was there, half a year ago, that it was in his thesis, and I had to check. You can get, so if you know he told me it's there, and I read the thesis and still didn't find it. And then I asked him again, no, he pointed exactly. Yes, the result is there, I can't read it. But so much of it was there much earlier. So continuity is true also for polynomials of higher degrees. This Gao and Chotze a bit later. So we know quite a bit about this for polynomials. And then the natural thing is, as I said, I have to hold the banner for transcendental maps. How much can we carry over to the world of transcendental dynamics? So the first question is, how can you deal with Hubbard trees? And that brings me to another interesting bachelor thesis, Michael Rothgang, who proved in his bachelor thesis two things: that post-singularly finite exponential maps don't have Hubbard trees, never. And then he constructed them. So, and that's, I mean, to show you a little bit about why there cannot be Hubbard trees. And this again, I do on the board. So you don't have critical, some of an ideal critical point somewhere at minus infinity, which maps to the singular value. And now if this is has a finite orbit, then at some point, perhaps, let me try to, at some point, the orbit of minus infinity, or the value is at 0, has to meet for some map of the form the lambda e to the z. So that means that there must be a point that has two pre-images under the exponential. So the distance between them is 2 pi I times an integer in order to have the same value. Why is this a problem? Let me use some color. We know that such maps still have dynamic rays. I don't want to give a precise conceptual definition, but these are curves. There's a curve that connects the singular value to infinity. And so that has the same mapping properties. The image of this curve is such a curve, is such a curve, is such a curve, and then perhaps they come back. So this is a pre-periodic curve, but all these points escape. You don't have a Riemann map around infinity through which you can construct these curves, but they exist anyway. If you have a curve that lands at the singular value, then this guy has countably many pre-images, so which starts at an infinity and connects it to minus infinity. And then you have another pre-image like so, and then another pre-image maybe here. So there are 2 pi periodic pre-images of this curve. All these curves consist of escaping points. Every point goes off to infinity. And now you want to have a Hubbard tree, which is a compact subset of the plane that connects this point, this point, this point, and this point. In particular, it connects 2 points that are 2 pi k apart. So they're separated by escaping points. So if you want to connect them, you have to go through escaping points. If it's invariant, it cannot be compact. Now you can try various things. One is you say, okay, if you don't want to go through escaping points, maybe you go somehow through infinity like this. You can try that. But then the pre-image of this point also has to go through infinity. And you suddenly get a countable dense subset of points on the tree at infinity. Well, in other words, there is no Hubbard tree for such maps. That's the bad news. The good news is it doesn't matter. What you can construct is, well, I'll show you on the next slide how you get out of it. The next problem is if you want to define bi-accessibility dimension. So by the way, bi-accessibility dimension has an advantage over the co-entropy approach. It works for every polynomial. You don't have to use a Hubbard tree. You don't have to use, well, the finite transition matrix. You don't have to use the assumption that the maps are post-critically finite. So it would be more natural to work just with bi-accessibility dimension. Unfortunately, in the transcendental world, there is no natural space of angles with a natural measure. So external angles for polynomials are just a natural circle with a measure. Here you can extend it, but these are, the external angles are like infinite sequences over the integers. And there is no natural invariant measure that makes you really, gives you a concept for the bi-accessibility dimension. Another problem is here topological entropy. Anna Benini, John Fones, and Han Peters investigated topological entropy for transcendental entire function, and they proved always infinite. So this is the natural analog of Misha's result of degree infinity. Topological entropy is always infinite. It's a nice uniform result, but it doesn't help you much because it doesn't, well, it helps you in one way, but it doesn't distinguish maps through their dynamical complexity. Often the Julia set is just a complex plane. And if you just see the complex plane, there's nothing much in structure that you can work on. So now let's try to get Hubbard trees for post-singularly finite transcendental entire functions. For some of these maps, like cosines, post-critically finite cosine maps, you can construct Hubbard trees, exponentials you cannot. And then David Pfrang, in his PhD thesis, introduced the term homotopy Hubbard tree. Shows every post-singularly finite transcendental function has a finite homotopy Hubbard tree. This tree is unique up to homotopy, and it distinguishes the given map from all others within the same parameter space. So it serves the same purpose for Hubbard trees, for polynomials, here in the transcendental world. Note, there is no assumption, no restriction on what class of transcendental maps you want to have, other than post-singularly finite, so all singular values have to have finite orbits. This implies, of course, that you have finitely many singular value. So you must be in a class that's known as Yeremenko-Lyubich class. So there is an implicit finiteness assumption, but nothing else in terms of these maps. So what is the difference? We just proved there is no Hubbard tree. What's the added value of a homotopy Hubbard tree? So the definition is the same, except you don't require that it is invariant as a set, but that you still have a tree, finite tree just as before, that connects the singular orbit and is minimal in a sense, but you have marked points like for polynomials, which are branch points, endpoints, and all post-singular points. And then the edges between them are defined only up to homotopy. So you don't want to know the exact set. There might be an escaping point. And then you just have to say it right, that this tree is invariant up to homotopy. And then it works. In hindsight, it's a very natural thing nobody cares about actual, well, it's not quite true, but usually for a polynomial, you don't need it to be exact invariant. The combinatorial type, which means the homotopy type, that's what you need. And in that respect, it is the same, whether or not you can make it fully invariant. And for instance, it's the basis of Thurston theory that we want to classify post-singularly finite dynamical systems. And here, Thurston theory is about turning topological data, such as trees, into analytic or geometric data. And all the input is usually up to homotopy. So this is a very natural condition from the point of view of Thurston theory. I'll give you a hint towards the end when we talk about combinatorics, how to construct this tree. But then, so when you have this tree, you can define core entropy just the same way. So finite tree, even though you don't have exact invariance, you still have the transition matrix. Every edge maps over one or several other edges. That gives you a finite transition matrix, and the log of the largest eigenvalue. It's the same definition that Thurston came up with. So once you have this homotopy Hubbard tree, you can define core entropy for post-singularly finite transcendental interactions. So then there are a couple of interesting properties. For exponential maps, for instance, core entropy is always bounded by log 2. And the same for unique critical polynomials of every degree. A priori, unique critical polynomials have the formula z to the d plus c, single critical point of high degeneracy, but only one. And this has surprised some, because you say degree d, complexity grows. And then for exponential, it should be even higher. No, I'll explain to you why in a moment. For exponentials, topological entropy is infinite. Core entropy in the post-singularly finite case is no more than log 2. For cosine, cosine is just a Möbius transformation away from exponential. You can have arbitrarily large core entropy. That's an observation by a former PhD student of mine, Bernhard Reinke. And for instance, pi times n times cosine, just you have n oscillations. The unit interval maps n or 2n times over itself. So you have n full horseshoes. And then it's a natural generalization of the Chebyshev map with log 2. You just get full oscillations. So there is no uniform bound in the space of cosine maps. Of course, as n tends to infinity, the maps tend to infinity. But life is much more interesting here. Core entropy is even locally unbounded. You have cosine maps lambda cosine z. Lambda are complex factors that tend to a finite limit in the complex plane, so that the associated core entropy tends to infinity. In fact, every parameter on the bifurcation locus of cosine maps is a limit point of such sequences. So every parameter in the bifurcation locus, you have sequences converging to it where core entropy goes to infinity. And you have other sequences where core entropy is finite, it's bounded. So it's as discontinuous as it gets. I haven't mentioned the name Roman Chernov. He has written his thesis about such questions. And then together with Bernhard, here's the result. This is an interesting phenomenon, but you can still try to prove continuity if you restrict, in a combinatorial sense, to bounded maps with bounded dynamics. Then, in fact, you have continuity. But of course, this is only a subset of two-parameter space. So you have some subset with continuity and at the same time intermingled unbounded values. So this is quite an interesting structure from the point of view of core entropy for transcendental mappings. So that, of course, raises the question, exponentials are uniformly bounded log 2. Cosine is so wild. So what's the difference? And then the question is, in order to explore this, how do you best define core entropy in different ways in order to be able to handle this? The log of the leading eigenvalue is kind of the classical definition for the transition matrix if you have a finite invariant tree. Another possible definition is you take a typical point in the Hubbard tree and you count how many preimages this has of generation 1, 2, 3, 4. This number diverges, and the exponential growth rate of the number of preimages in the Hubbard tree is, in the post-critically finite case, is again core entropy. An interesting special case that we will work on is the number of pre-critical points. So just preimage is not of a random point, but of a critical value. And you count how many there are of given depth. And then the intuition is the number of combinatorial different orbits of length n in a given Hubbard tree. And again, it's the exponential growth rate. So if you have the Hubbard tree and you just cut it in the quadratic case, cut it at the critical point, there's a critical value here, there's a ray landing, so the two pre-image, this is degree 2, the two pre-images are rays that land at the critical point and that subdivide the complex plane, which you can label by 0 and by 1. And then every point has essentially a unique itinerary 1, 0, 0, 1, depending on, or left and right, depending on which sides you visit. And so then the number of different possible sequences that you get, well, exponential growth rate. This again is core entropy. So again, it's the number. This is just a repeat. My favorite definition, or one that we actively work, all the papers on this topic intermingle different definitions. They're sometimes better from different points of view to use one or the other. So the number of combinatorially different orbits in the way on the Hubbard tree or in some interval, whether you take the whole Hubbard tree or you just take a particular interval, maybe this one, and then you take the max for all intervals, it's pretty much the same. It's a bit annoying to go back and forth. This is multimedia at its best, but not at its best, but kind of active, going back and forth. I have to, yeah. Sorry, this is how it is. So you start with an interval, and you map it forward, and the image interval might be here, and at some point the image interval will intersect the critical point. And then you note, so pre-critical point is taking pre-images. Here are computed by taking forward images on this interval. Map it forward until it hits the critical point. Then I have to cut it because it will no longer map forward injectively. So I take one half and I take the other half, and I do this separately. This half might go here, and so on. So by mapping it forward, I will eventually find all pre-critical points on this interval. You map forward until you hit a critical point. So this point here hits the critical point, so you have a pre-critical point of depth 2. And well, so that way, recursively, you find all pre-critical points on this interval. And you count them. And that is a definition for core entropy. And now if you only have a single critical point, then starting with the interval, every step you can subdivide it only into two parts. And then you take this part, and in the image, again, you can subdivide it only into two parts, and again. So as long as there is a single critical point, the number of pre-critical points to produce like this is no more than 2 to the n. And then log 2 to the n is n log 2, divided by n, so the entropy is at most log 2. Even if the critical point has many branches, which is true for the unicritical case. And even for the exponential, you have in some sense a single critical point out at minus infinity with infinitely many branches. Every interval that you map forward will get cut at most once in every step. And that by induction shows that there are no more than 2 to the n different orbits or pre-critical points. So that gives you the bound of log 2.
When you say exponentials with an S or an exponential family, what were you?
Lambda e to the z. Yeah, and lambda, well, it's usually a complex number. Which in some sense are the limits of unique critical polynomials. Well, if you write z to the d plus c, you have a critical point at 0, critical value at c. That doesn't really have a limit when d goes to infinity. But you can rewrite it as lambda 1 plus z over d to the d. It's the same map for the right choice of lambda. Here the critical point is at minus d, the critical value is at 0. And then you have a limit. The limit, critical value is 0, and the limit is 0. The critical point drifts off to minus infinity. And then you naturally approximate the exponential. Well, for the polynomials, it makes little difference. But critical point at 0 with ever higher criticality doesn't have a reasonable limit at the origin. Make sense? So this is the explanation why you get this uniform bound log 2 for exponentials and not for cosine. Cosine has infinitely many possible critical points, and if they're all aligned, if you make use of them, then entropy can get large. So this is specifically about exponentials, and then Malte Hassler, I mentioned him before, asks, so what are the natural spaces of transcendental functions for which you do get a uniform bound of core entropy? And the natural answer are structurally finite and transcendental entire maps. This is a very nice family to work with. Various people have worked on it in various aspects, but let me first define them. They structurally finite means they have finitely many critical points and finitely many degenerate critical points at infinity, which is called asymptotic tracts. Like for exponential has an asymptotic tract at minus infinity, which is an infinite degree critical point out at infinity. Maybe I should define it differently. A singular value is a value that has no neighborhood on which all pre-images are univalent. Usually you have a disk around the point, and then you have countably many pre-image disks. This is a regular value. And if it's a singular value, it could either be a critical value, like for polynomials, or like for exponentials, there could be a curve to infinity with values limiting to this point, like for the exponential. So finitely many critical points and finitely many asymptotic tracts is the definition for structurally finite. And then back in the days, Nevalina, 18th century or early 19th, no, 19th, early 20s, that way, yes. Every structurally finite entire form, these functions have the form integral polynomial exponential times another polynomial. Critical points, well, you take the derivative, that means the integral vanishes. So zeros of this polynomial are critical points, so the degree of S tells you how many critical points you have, and then asymptotic tracts are coming out of this polynomial, P. And therefore, I'm not sure whether therefore is justified. Arguments like this show that the core entropy for such a map is bounded by log of degree of the lower polynomial plus degree of the upper plus 1. So exponential specifically, you have, this polynomial doesn't exist, so it's just, well, 0 plus 1 plus 1 is log of 2, and as I said earlier. And of course it can happen, like for unique critical polynomials, that several critical points or asymptotic tracts coincide, and that improves the bound. So let me go to unbounded entropy for cosine maps. I mentioned before the n times pi times cosine z. Well, more specifically, the Hubbard tree is this interval. And it maps to itself 2n times. So entropy is, well, actually log 2n. So this is, I had mentioned this earlier, but the research results that really in the cosine family, you have control of how to get entropy towards infinity. And then the question is, so there's the structurally finite ones with uniform bounds, the structurally infinite ones, and then the other ones like cosine with infinite bounds. What kind of bounds how can you see whether they're better bounds? For instance, well, the exponential, here I wrote it out, the second iterator of an exponential, lambda exponential of mu exponential of z, this is the second iterate, and everything there is infinite. So you have infinite many asymptotic tracts. So in some sense, you have infinitely many generalized critical points. So the estimates that we gave you before might allow infinite core entropy. But it's the second iterate of a map with entropy log 2. So the entropy as a second iterate can only be twice as much. So the entropy is really only 2 log 2. How can you understand that even though you have all the critical points available, you don't get big entropy? And that's the next observation of Malte. If the maximum number of generalized critical points on any interval in the Hubbard tree is S, the stress is here an interval, then coentropy is at most log S plus 1. So critical points have to be aligned. Dima?
Can you replace this theorem S by the number of physical orbits?
I don't think so. I don't think so. If you have an improvement, we can discuss it afterwards, but I'm not very, at the moment, I don't see that this makes it better.
So that to respect the physical relations. You said that if there is a physical relation, then there is a proper entropy.
Yes. Well, you count critical points with without multiplicity, just the points, no matter whether they have higher degrees. Maybe we can improve it afterwards. And so if you look at this 4 exponentials, so I want to draw a picture again. So the regular exponential has, well, at minus infinity, so here is minus infinity. You've never been so close to it. You may have infinitely many branch points. Branches at this one point, and the second iterate has pre-images of this guy everywhere. So you have lots of pre-image points of infinite degrees. So you have infinitely many generalized critical points. But in order, so you have an interval, you want to map it forward and subdivide. Every interval can at most, when you go like this, get cut once, twice. It gets cut only 3 times. So 3 plus 1 is 4 entropies at most log 4. So just having many critical points around does not mean you get high entropy unless they're aligned somehow in the Hubbard tree. If we had more critical points somewhere in between, that might give higher entropy. But this way, the structure of the Hubbard tree, even though you have all the critical points, the structure of the Hubbard tree gives you a limitation for what the entropy could be. And that, of course, leads to a challenging question. You have your space of maps, which means you know how many critical points, critical values, asymptotic tracks, and so on you have. How can you assemble them in terms of Hubbard trees so that entropy is this or that? Because it all depends on what kind of Hubbard trees you can construct. It's easy to draw Hubbard trees with all kinds of critical points and connections and whatever, but are they realized? Well, we know from David Pfrang's thesis, the homotopy Hubbard tree is realized. We don't care about the homotopies. So in principle, every such map has a Hubbard tree. But the much harder question is, given such a potential Hubbard tree, is it coming from a map? And that's the big topic of Thurston theory. It made it into the title, but I don't think I have time to get into it. Probably not. But even these questions are calling for an extension of realization theorems. You input the combinatorics, such as Hubbard trees, which maps are realized. I should have mentioned here, I don't think it's on the slide or this or the next. Sergey Shemyakov has worked on this. He defended his thesis about 2 years ago. He gave an answer for structurally finite entire functions. There he has a realization theorem that given a topological candidate, it is realized if and only if, and the same criterion by Thurston actually holds, no Levy cycles, like for polynomials. But of course, the original Duody Hubbard proof doesn't work. So this is another thesis, but not so much the topic of the talk today. In the last minutes that I have, I would like to talk a little bit about combinatorics in some order. And yeah, I was trying to start from the back. In order to define core entropy, the number of pre-critical points of depth n, and then, as I said, count the exponential growth rate in the sense you take the lim sup of the log of this number, and that's core entropy. But what critical points do you take? Do you take all of them on the Hubbard tree? Do you take all critical points on a linear subset or an interval on the Hubbard tree? Or you can take it between two singular values. It's all the same when you have finite Hubbard trees. So in the post-singularly finite case. But when you want to discuss questions such as continuity, or even define it beyond the post-critical finite case, these answers might be different. Remember, for polynomials, you have Hubbard trees in the post-critically finite case. And in general, it's not so clear how to set it up. Of course, once you show continuities, the continuous extension, any continuous extension is unique if it's well-defined on a dense subset. By accessible dimension is a way to give a natural definition along the way. And now what can we do here? In the post-singularly infinite cases, Hubbard trees may still exist. I'll discuss this for quadratic polynomials in a moment, in a purely combinatorial way. But when you have infinite trees, you have the tree, you can count pre-critical points, pre-singular points on the tree also. But even for quadratic polynomials, it may happen, so when the critical orbit is somehow dense, in the Julia set or wherever, it may happen that pre-critical points on the Hubbard tree, there are 2 to the n of them, so entropy wants to be log 2. But in that case, it's just the wrong, well, it's the correct answer to the wrong question. So you shouldn't take pre-critical, when the tree is infinite, pre-critical points on the Hubbard tree are too many. So really you should restrict to linear subsets, and then perhaps take the supremum over all linear subsets. So even for quadratic, as I said, there are many polynomials with infinite Hubbard trees where fake entropy would be log 2, but that's not the interesting concept. And then Malte has an example of exponentials. This is whatever combinatorics, leading sequence or whatever. If you look at this, you get a tree with infinitely many branches like this one. And then for every depth, the number of pre-critical points is infinite. So not just is entropy infinite, but these quantities for every n are infinite. And then take a log, which is infinite, so everything is infinite for a particular example of an exponential map where entropy should be log 2. So really, it very much matters where you measure, take the pre-critical points. And if you wanted to take an infinite, well, extension of a transition matrix, again, you have to be careful that you don't get too much. So this is a bit tricky, but then, well, there are various definitions that we have that lead to the same reasonable definition of core entropy, even when you have infinite trees, even for transcendental mappings.
In the terms of the formula there, I guess you have the missing leading 1 over n for the log for the core entropy.
Yes. So this is, take this as a half fraction of 1 over n. Yes, you're right. Thank you, Carsten. So I have a few more minutes, I think. Yes. So let me try to tell you a little bit about how to use combinatorics to reduce everything to a purely combinatorial question and tackle things in a combinatorial way. And that I will do live on the board, in particular the triad argument. So what will I erase? So this is going to be the same picture again. So I have, let's say, a quadratic polynomial to make life simple. And then you have whatever Hubbard tree, here's the critical value. The critical point cuts it into two parts, which we label 0 and 1. And then the needing sequence is the sequence, well, just easier font 0, 1. This is the sequence the critical orbit visits, starts at 1 by definition. So this is a sequence over 0, 1 that describes the critical orbit. How can you, just knowing this sequence, how can you reconstruct the tree? So I take, for instance, the critical value here. Then I take, this is nu1, I take nu3, and perhaps a point nu7. So I want to find, for those 3 points, are they in the set that they connect? Where's my orange? Here. I define a triad, the set that connects those 3. So there are various possibilities. This could be aligned, that the 3 points are aligned like so, and then either one of those three could be in the middle, or this could be a non-degenerate triad like so. So I want to find out for any 3 points, post-critical points, whether this is a Y-shaped triad or whether they're aligned, and if they're aligned, which one is in the middle, which one's in the end. So the triad argument, and I said it's a democratic way to do it. I take this is a Y-shaped triad. I take the image, which may be here, and then take the image, which may be here, and eventually it has to cut the critical point. So the image may be that. And I can tell as long, so the 3, this is needing sequence, what did I say? 1, 0, 0, 1, 1, 0. The nu3 is the second iterate, so it's the second shift. And this is the 6th shift. So knowing the needing sequence, I also know the itineraries of the other points. And if they start with the same symbol, 1 in this case, well, I know that the triad maps forward homeomorphically because they're both on the same, all 3 on the same side of the critical point. So I delete the first entries in all 3. Then I have the image triad. And again, I look at the first entry in those 3. If they are the same, the map forward homeomorphic, the shape is unchanged. And when it cuts, then I know one of them is on one side. It starts with a 0, and these start with 1. Then I cut. And the one which is here on the end, I know which of the 3 sequences that is. And that's an endpoint of the triad. And then I cut at the critical point, map forward injectively, and I can repeat. And so I have these 3 points, nu1, nu3, nu7, just looking at the needing sequence. If eventually all 3 are cut, then the triad is Y-shaped. And if not, then I cut only one and the other, and never the third. Then I know the one which is never cut from the other is the middle of a linear triad. So in other words, the needing sequence alone tells us the structure of how the tree is, how the endpoints of the trees, the post-critical points are aligned. And from this, you can reconstruct the tree. This is the idea in a generalized context of what David Pfrang does to construct the homotopy Hubbard trees. Oh, I missed the democracy. Why democracy? If I want to find the itinerary of the branch point, if it's a Y-shaped thing, then, so as long as the 3 entries are the same, the branch point is the same. I just copy the entry. And when it hits the critical point, one is different from the other two. So I cut off the different one. And the branch point, well, you have 2/3 majority on this side. So the branch point always goes with the majority. And democratically, the 3 orbits decide on their common agreement. It's the itinerary of the branch point. So that way, you can not only determine if the triad is a Y, but you can find by democracy the itinerary of the branch point. So you find all the branch points in the Hubbard tree. And if you do this properly, then what David does, he takes all the post-singular points. He has a more general setup of the combinatorics, but still he determines for all of them which ones are endpoints. And he finds all the branch points using democracy. And then I had it here earlier. The tree is determined by the endpoints and by the branch points. And that you get purely combinatorially, and then you can connect them, well, the way you just combinatorially. So you have the points that you want to connect, and then you know which ones you have to connect. The homotopy doesn't really matter. So therefore, combinatorics tells you everything except of the homotopy. So you get the homotopy Hubbard tree once you have the right combinatorial setup. I would like, so this is David's thesis. I would like to return to Malte Hassler's bachelor thesis to construct a Hubbard tree. And that's been an interesting experience. I spent many, many months discussing with Henk for quadratic polynomials with finite singular orbits, how to construct the tree out of a leading sequence. And Malte has a much more elegant way that does not even require things to be post-critically finite. So if you look at the combinatorics the right way, it's all very easy. So you have the critical value, which is the leading sequence. You only know the leading sequence. Here you have the critical point. The itinerary is a star. And then it maps to the critical value. So the itinerary is that. And in the same way, like for the triad argument, you find all pre-critical points between critical point. We call this the critical path. On the critical path. So you compare the itineraries of those two guys. As long as they're equal, this maps forward homomorphically. And when they're not equal, you find a pre-critical point, the first pre-critical point between those. And you know the itinerary of this, whatever it is. And then you iterate this interval and that interval. And you find pre-critical points here, and so on. So purely combinatorially, just in terms of the leading sequence, you can find from the leading sequence all pre-critical points on this critical path. And then the critical path is just a closure in the right topology of all the points you constructed. So there's a very simple, you don't have to understand the details, but there's a very simple way to find a dense subset of combinatorial points between critical point and critical value that describes the point in between. That's not the Hubbard tree, but the first step is the critical path out of the combinatorics. And this you iterate forward, the critical path, and the image of the critical point, this guy goes here, the image goes there. So the Hubbard tree is just the tree is the union of the nth iterate of the critical path. And that's it. Of course, you have to show it's a tree, you have to show whatever. It can be a finite tree, can be an infinite tree. But so just out of combinatorics, you get the tree, you get all data, you get all combinatorics. And if you do this the right way, then you can extract all the dynamical properties in the entropy out of a purely combinatorial approach. I have a few slides which I can just flash at you. I know my time is up. the ones that I skipped, you can, just to show you it exists, I'm not going to go through it. In the general setting of a transcendental entire function, you have singular values, you have preimages which are tracts. You can just extract from the map a purely combinatorial set of angles that play the same role. Here the singular value is the landing of a ray, and they have two preimages, so on. You need to find rays that land at all singular values. You don't even have to have rays. Sometimes radones exist, and you take filaments, sometimes known as dreadlocks. They don't have to land, it all doesn't matter. You just need the combinatorics of those that should land. And out of a natural combinatorics, you can define core entropy for every transcendental entire function. No restriction on anything. Of course, if you have infinitely many singular values, you should assume that the core entropy is infinite. But if it's finite, it's a purely combinatorial setup to define it all and deduce the properties that I mentioned earlier. I haven't proved all the theorems. But this is kind of the spirit of a forthcoming work with Malte that I wanted to advertise here. Thank you for your attention.